random stable maps, geometry, percolation, and simple random walk.
Thanks a lot. Thanks a lot to the organizers for this invitation and the organization of this wonderful workshop. I'm maybe not the only one to have the impression that the first workshop was just yesterday. I think really, but then I look back at the dates, and I had no daughters at that time, and when I look at the picture, I see that some stuff has happened in between. And not much on my side, but I'll try to describe. Should I? Does that work? Okay. 1, 2, 1, 2. Should I start again with the joke or directly with the math? Okay. The jokes have not been recorded, but anyway. Okay, so to answer Scott's question that he will ask at the end of the talk, what is the promising future, blah, 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 there is still at least one thing that we don't know how to pin in this planar map world and so on. These are these decorated planar map stuff. And so random stable map are one way to try to approach this using Gasket decomposition. There are these random stable maps, they are contained in a map decorated with ON model, and so it's a proxy maybe to understand their geometry, but I will try to convince you that they have some intrinsic beauty in their own. Okay, so maybe you all know the setup, but since I was not here last week for Gregory's talk, I will try to recap what I will need. So Boltzmann discrete stable maps. So what's the setup? So we'll work only with bipartite maps. I guess that Gregory was also using this, meaning that all degrees of faces are even, and we have a weight sequence Q, Q1, blah, 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 that we use to build, yes? There are many rooms in the front row. Come. But you can hear what I say, right? Okay, so Q1, but this will just be the recap board. It won't be very useful. And we have a weight that we assign to each map M, just the product of all the weights on degree of faces for F faces of the map. What does that mean? That means that if you take a map like that, I don't know, rooted here, then you've got a face of degree 4. This will receive a weight Q2. This is a face of degree 6, so weight Q3. This is weight Q1, and you've got a weight for the external face as well, maybe Q2. Okay, that's the setup. And as usual, so that's called the Boltzmann measure. And we'll assume admissibility. What does that mean? Admissibility just means that the total mass, all maps, is finite. We'll assume criticality. So this is a bit more subtle condition that that is equivalent to asking that under the Boltzmann measure, the square of the size of map is infinite, blowing up. You may have thought that criticality is the expectation is blowing up, but no, it's a second moment. And we'll assume that they are discrete stable. So I don't want to enter the exact detail of discrete stable, but you all know that in words of random walks, increments, if they are finite variance, if they are centered is criticality. If they are finite variance, then you are in the Brownian universality class. And if they have a tail which is decaying polynomially, you are in the discrete stable setup. But okay, here you need really to enforce criticality and the fact that you see this stability. So I will just one way to say it. It's not the definition, but one way to say it is once you have these two conditions, you can define the model M infinity of infinite Boltzmann planar map. So this has been done in this context by Björnberg and Stephenson. And also independently by Stephenson for the non-bipartite case. And once you have this infinite model, this discrete stability condition is equivalent to asking that the probability that the root face of this guy has degree k, that this decays like k to the minus a plus half. And from this, you see that you need to have a in between 3/2 and 5/2. Okay, discrete stable with parameter a in 3/2, 5/2. Okay, so what does that mean heuristically? Okay, the root face is the face, say, adjacent on the right of the root edge, so it comes with size biasing, right? It has been picked according to the number of edges it has on the boundary. So if you remove the size biasing, it's the same as asking that the typical face, say, in the UIPT is alpha stable, where alpha is just this guy. Maybe I will use it sometime. Alpha is between 1 and 2 and is just equal to a minus half. So it's equivalent to asking that the typical face has a degree which is alpha stable, right? So you expect that when you see such random maps, you will see large faces in the scaling limit. Okay. So I guess that Gregory was discussing that last week, so I will not spend much more time on that. And try to put this in the context. So what is this? This is a ON decorated map. So to be precise, if we really want to stick to what is known, you have an ON model, a rigid ON model. I look at the slides of Gregory, he was discussing that. So rigid ON model on quadrangulation. So rigid ON model on quadrangulation. So this was studied by Boro, Boutier, Guiter. Okay, so you can define the annealed model of a planar map together with ON configuration on it. And of course, you will always deal with the critical one. You tune the parameters so that this is critical. And this is the object we are all after. I mean, we don't understand the geometry of this guy. But what is known is that if you take the gasket, so taking the gasket is equivalent to, you have the root edge sitting here, and you remove everything that is inside the loop that you see from the root edge. So your map will now look like something like this. You still have the first generation of loops, but you have nothing inside. Okay, and your root edge sits somewhere here, and nothing inside. You have performed some surgery. Okay, and as Gregory was describing this, it's fairly easy to see that this model of random map that you get here is a Boltzmann model with the weight corresponding to the partition function of ON decorated map with a boundary. And when it is critical, then exactly this is an A-discrete stable map, meaning that, well, you will have large holes. A-discrete Boltzmann map. Stable Boltzmann. Okay? Boltzmann map. So, just to summarize, it is just that this model appears as the gasket of these more general maps. Okay, but when you have the ON model, you have two phases. You have the so-called dilute phase. You can tune the parameters here in two ways, and you have the dilute phase and the dense phase. And the difference between these two phases is that the boundary of the holes are self-intersecting and intersecting each other with positive probability in the dense phase, but not in the dilute phase, right? Okay? In the dilute phase, these are simple holes. Okay? So that's on the planar map side. And there is the LQG side. The LQG side is this conjecture that if you uniformize this map, not the one with the holes, but the map with the ON model on it, then you should get some CLE here, some CLE there, with the CLE with non-intersecting loops here, and CLE with self-intersecting loops there. Okay, so that's the picture that Wendelin was describing, and that maybe some other people have described during the workshop. And so here we've got a parameter n, which varies in between 0 and 2. That's the parameter n of the ON model. Here we've got a parameter a that ranges between 3/2 and 5/2. And here we've got a parameter kappa that ranges between 8 and 8/3. And there is this relations that I don't know by heart, but maybe Bertrand does.
N for -2 cosine 4 pi over kappa.
Good. So A is 2 plus or minus, depending on the phase you take, dilute or dense. It's the same, 1 over pi r cos the n over 2. And kappa, and A is 1 plus 4 over kappa. So let me just do some sanity check and some examples and some particular cases. So if you take A is equal to 5/2 here, 5/2 will correspond here to 8/3. What are you supposed to see here? You're supposed to see Brownian map here, because the holes are very, very small. They disappear in the CLE. You get to the limit of 8/3. So here it should be Brownian map. There is a critical case. Kappa is equal to 4 corresponds here to n is equal to 2. And corresponds to A is equal to 2 as well here, where the holes are not self-intersecting, but almost. And here there is the kappa is equal to 8 space filling case, corresponds to, on the planar map side, it's A is equal to 3/2, and this is, roughly speaking, CRT, meaning that the maps, they will become tree-like in the limit. So that's the general picture. And so, if you believe in the conjecture up there, if you believe, well, this has not to be believed, this has been proved in the case of rigid ON model. So you think that there is a link between these stable guys and the CLEs. Okay? Question on that? All right. So now my goal will be to study directly in the planar map side these objects, and I will first recap what is known on the geometry of those guys. So let me make the same picture. So A ranges between 3/2, 2, and 5/2. So when you are at 5/2, the root face has a heavy tail, but very light. It's almost finite variance. And so what you should see is a map with small holes only. Small holes that disappear in the limit, and that should be Brownian map. That should converge to the Brownian map. And this has been proved recently by Cyril, for example, in the largest generality is the one of Cyril. So in between here we have map with big holes, but they are not intersecting, sorry. We've got the guy here. We've got the guy here with self-intersections. And here tends to be almost tree-like. So maps like that. Okay? So what is known is the diameter of these spaces. So to fix notation, I take Mn, a discrete stable map, which has the Boltzmann law, WQ, condition on having size n. Think of number of edges, for example. So you sample such a guy, and you ask, okay, what is the diameter? So the diameter is n to the 1 over 2a minus 1 in the dense phase. And the same here, 1 over 2a minus 1. So you see that when a is 5/2, 5 minus 1 is 1/4. So it's the halves of dimension 4 that we all know. And this has been proved by Le Gall and Lirmont in the paper where they introduced this model, Le Gall and Lirmont. So we know what is the order of magnitude of the diameter, and they've got subsequential scaling limit known as the stable maps, which hence have halves of dimension 2a minus 1. Yes?
Is it known that the large faces don't touch on the right and scaling grid? And they
Not quite, no, not exactly. What is known is that if you take one face, you take it out of the map, then itself, it will be self-intersecting in this regime. It looks like a loop tree, and here it looks like a circle. It's not the same as looking at the face embedded in the map, but yeah. Morally, you have, it's not quite established yet, but you have a phase transition in the topology. So here, phase transition in topology.
Not with respect to the distance, you mean?
No, yeah, distance.
It doesn't exclude the fact that some...
Exactly, but you will see, it's exactly my point. There is still some room there for a phase transition in the distance. So that's for the model Mn. But you may very well look at the dual of Mn. What is the dual of Mn? Well, when you have a map, you can take the dual map by putting a vertex in each face and consider faces as vertices and vertices as faces, exchanging their roles. But if you do that, then what you end up with are maps not with large faces, but with large degree vertices, right? They are kind of hubs with many, many arms. So in the dense phase, these hubs will have the additional property that two big hubs, two big large degrees, may share edge in common, and there are many multiple edges, loops, linking a hub to itself. It's the same as self-intersecting. Okay? And so what we proved a couple of years ago, but that was not proved at the first random geometry program, right? It came after. The result with TIM, that the order of magnitude of the diameter is a minus half over a minus 2. Yes? Tim, you know a minus half. We'll okay? And so it's good because when a is 5/2, you recover n to the 1 over 4. So again, Brownian map. And this is known in one case for triangulations work that I did with Jean-François. So it's a consequence of this more general work. But so in the Brownian map case, taking the dual should not affect too much the distances. But there you see that there is a phase transition at a is equal to 2 because this dimension is blowing up. And so the diameter of those space a minus 2 over a minus 1. Well, you nodded, right? Cyril was like... But here there is a phase transition, and then the diameter is not polynomial anymore at a is equal to 2, and actually it becomes logarithmic in the dense case. Well, you may expect this because you have many hubs connected to each other, which enables you to travel far away with short distances. And actually, at a is equal to 2, something interesting is happening. It's a work that we did with Cyril and Timothy. So then it's log squared of n. Oops. Do you get me? Okay. I will pay for that. Okay, log squared of n. Okay, once you see this exponent, you say, okay, there is no hope to get a scaling limit because of this logarithmic rate of growth of the diameter. I mean, there are no space that if you rescale and have logarithmic diameter, you've got a scaling limit. Here, there is some hope to get a scaling limit, and at least this is connected and to a program that we have with Igor Korczynski and Jean Berthoin. So Berthoin, Igor, and Timothy also, Bud and Korczynski. So the description of the scaling limit is related to this gross fragmentation process that nobody has described and that I won't describe today. Again, sorry. Okay, this will work. And here, you don't expect that there is a scaling limit for the full map, but there is something. There is something. I will be vague, but there is something. I will be vague because I'm not sure myself of what to state, but for those who know, it's related to this CLE4 metric that we heard about 3 years ago, but that is still not yet out. So there is something related to planar maps at this stage. Okay? So still some work here because we got subsequential scaling limit. Still some work here to get the scaling limit. And the scaling limit here should be homeomorphic to a sphere because this just pinches the metric, but it does not create holes. So here we expect to have stable spheres in the limit. Questions on that? No? Okay. So if there are no questions, then I'll move on to percolation. Percolation. So what do we want to do? We want to do percolation on those random graphs. So very easy. You first sample your graph, and then you do percolation. And we can consider Bernoulli percolation, so everything is independent, but we can consider phase percolation, you color the faces, side percolation, you color the vertices, or edge bond, you color the edges of your map, black or white with probability P. This is not very well understood yet. It's understood in the case of quadrangulation. Yes?
Go back to your thing. So when you say no scaling limit and with the logit, I mean, you should get just the distances between the clusters. Right?
Yes.
I mean, just the integer distance.
Exactly, integer distances. Yes. Yes, integer distances. Totally. But yeah. But this integer distances is really, well, you see the lattice in the limit, so well, it's not what I would call the scaling limit, right? It's good. But there is some interesting distributional limit, but not a scaling limit in the sense that you would expect. But you're totally right. Okay, so I will not focus on side percolation because we don't yet know how to handle it in full generality, but those two percolation process, phase percolation and bond percolation, are understood in the generality of Boltzmann map. And so there is an almost sure percolation threshold that I will denote P, C, Q, because of course this depends on the model via the weight sequence Q, PC bond, and PQC phases. Almost sure percolation threshold that are in 0, 1, let's say. What do I mean by almost sure percolation threshold? So there are different ways of characterizing that, but the most natural way is to say, okay, consider the infinite model of map that we introduced there. So that's an infinite graph. So on this infinite graph, you can define percolation threshold, the smallest p, so that there is a positive probability to reach infinity from the origin. Okay? And it turns out that these percolation thresholds, which depend a priori on the realization of the graph, are actually almost sure, meaning that they do not depend on the realization of the graph. It's an almost sure random variable. Okay? So they are defined on this guy. Okay, so what do we know about this percolation threshold? I will be a little bit loose, but we know them. So they are explicit in terms of Q. And take very nice form if Q, for example, has a nice form. And so what do we know? Let's do our usual diagram, A between 3/2, 2, and 5/2. And let's look at PC bond and PC phase for Q. And what you can see is that here the percolation threshold in the dense phase is 1. Because there is no interesting phase for percolation. Why? Because sorry, I should be here on M, not M star. You may say, okay, but that for bond percolation is the same. Yes, not for phase percolation. I'm working on M. Okay, so there is no interesting phase for bond percolation in the dense phase. But here, that's interesting. PC bond is computable and belongs to 0, 1. Okay? And it tends to 1 when the parameter A of stability tends to the critical one, tends to 2. You may say, yeah, but that's not very well defined because Q is an arbitrary sequence and being astable is just an asymptotic property on the Q's. Yes, but let's say that you vary this continuously in a nice manner, and one manner is to take Tim's explicit family of Q's that are astable. So it tends to 1. Okay. So you have an interesting phase for percolation there. And something interesting as well happens for phase percolation, because again, here you have no interesting phase for percolation for the dense guy. Well, you may expect this. Here at A is equal to 2, there is no interesting phase. But if you let 10P towards, if you let 10A towards 2 and look at the percolation threshold for phase percolation, actually it does not tend to 1, it tends to 1/2. So again, there is something that we have not completely understood yet. There is something that we're working on, there is something here, and I would like to say that at the critical point A is equal to 2, phase percolation is almost self-dual, almost. Not in a strict sense, because the percolation threshold is 1, but it tends, I mean, on finite maps, you see something really happening at 1/2. So there is still something to be elucidated there. Okay. So that's for percolation threshold, and then since there is an interesting phase for percolation in the dilute regime, you may very well consider the behavior of the cluster of percolation in this dilute regime. So you take M, your Boltzmann measure, according to your Boltzmann measure, so it's a Boltzmann map. You suppose that it is A discrete, A stable discrete, A discrete stable, with A in the dilute regime between 2 and 5 halves. You perform P bond Bernoulli percolation. And you look at the cluster of the origin that I will denote C of P to and put an emphasis on the dependence on P, so the cluster of the origin.
May I ask you a question?
Sure.
If you look at the UN picture, in the dilute case,
Yes.
when you do this phase percolation,
Yes.
means you have at most one site occupied for in each loop, right?
So this phase percolation is, you see that you, since the big phase they can touch, you see directly, I mean, morally that PC must be 1 because.
I'm thinking of dilute.
Dilute.
So you have these
Yes.
in the UN model.
Yes.
So I mean there you have at least 1 point, right? They don't.
Yes. Yeah, but since they don't touch, there is no obstruction of to having an interesting phase for percolation.
But everything happens on the gasket.
Everything happens on the gasket. But these big holes, I mean, okay, if you have a big hole that has been colored black, I mean, for white interface, that makes life hard, right? If you're white and you're here and you're stuck by a big face, and so it's not peanuts, I mean. But there is still some randomness inside, and it's related to Vendelin what was saying, but let me state the proper theorem. So we look at the cluster of the origin, and it's easy. This is a Boltzmann map. This is a Boltzmann map. Not very hard to see. But what is interesting is what is the type of Boltzmann map we get. And now let me vary P. So there is this percolation threshold depending on Q, 1 and 0. And okay, if you're supercritical, and we look at CP. If you're supercritical, you think that you will color almost all of the map, and the cluster you will get looks like the map itself. So here it's A stable. It's natural. When you're subcritical, you will color a very small proportion of the map, and you believe that your cluster will be very small, and actually the map is subcritical. Subcritical in the sense that this condition is not verified, that you have that the second moment is strictly finite, and actually you've got exponential tail for the cluster, for the size of the cluster. Okay? But what happens at the critical threshold? So let me remind you that the critical threshold was defined on an infinite map, but here we are performing percolation on a finite map. But this map, they have polynomial tail, they can be big. And what happens here is that we have another stable map of parameter A over A minus 1. That means that, and if you look at A over A minus 1 when A is between 2 and 5 half, this belongs to the dense phase, something like, I don't know. Let me put, I don't know, but when it's 2, okay, when it's 5 half divided by 5/3, something like that. But that's strictly contained in the full interval of dense thing, which is 3 half, 2, okay? And 2 you cannot reach 2, but 5/3 you can reach it. Okay? And now what is interesting is that if you like to play with numbers, you take this relation up there, while A is equal to 1 plus kappa over 4 over kappa. And this is, if you take this relation, you put it through the relation with kappa, this is exactly the kappa prime is equal to 16 over kappa Duplantier duality relation. So that means that if you take a stable map dilute, which is like the CLE for some kappa, which is below 4, you perform percolation in it, you look at the cluster, then you will get the map that corresponds to the CLE that is dual via this duality relation. Okay? But that's totally a statement in planar maps, and we don't use anything about these embeddings or nothing. It's just something using a stable random walk type argument and duality of stable processes. But let me put the emphasis that this is quite surprising that this holds at the discrete level exactly. I mean, it's not a particular sequence Q that comes from an ON model for which you may expect that this will hold because of all this machinery. It's already true in the discrete level as long as Q is well behaved and is astable. So it's a kind of striking universality in the planar, percolation on this planar map. Questions about that? No? Okay, let me move on then.
Subsequential limits, or pairs, or coupled?
No. We cannot hope for that because typically it's a Boltzmann map, so typically it's small. So you would first like to condition the first one to be large, but even if the first one is large, it may happen that your cluster is small. So you see, if you do critical percolation Z2, look at the cluster, it may very well be small at the cluster of the origin. So you want to both condition, but what you would do, you would like to see all clusters at the same time, blah 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 blah. But okay, no, this does not follow directly. Yeah, there is one technical step further, but. For example, from this you get conjectures on the size of the largest cluster in a Boltzmann map, but we have not proved yet that if you take a Boltzmann map condition to have n edges, perform percolation, look at the largest cluster, then the diameter of this is blah blah blah. This is not proved yet.
So what you're saying that if you discover, say, one of these of the percolation clusters, then you don't. The law of the rest that remains to be discovered is
a bit biased. A bit biased by the perimeter of what you have discovered, but not that much. So you should be able. But I mean, it's a 30 pages long paper. We have not. It's a humble step. Okay, 1, 2, 3, 4. Last topic I want to discuss is simple. Okay, so no, just to put. There are open problems. Many open problems. One is this, and the other one is what is this strange thing happening here? Okay, now simple on the MOOC. Sorry, I should have put a name here. Of course, this is joint work with Loïc Richier. It was written up there, but this was, I said it orally that this was with Timothy and Cyril, and this is with Loïc, and this part is joint with Cyril. Disclaimer, this is work in first stage of progress, so, but since I like it, then I was willing to show you what we have so far, but it's really preliminary, even before preliminary, it's just first look. Yeah, let's say first look. Okay, so what's the setup? Now we want to do simple random walk on this object, but these objects, so far I was considering only finite planar maps. If you want to do simple random walk, it's better to work to walk on the infinite guy. So we do simple random walk on M infinity, starting from the root edge, from the origin. Okay? And we'll also perform simple random walk on the duo.
Walk along the faces or along the face?
Edges, always. But if you walk on the duo, it's exactly performing the walk that you described. Again, starting from the origin. And we'll be most interested in the displacement of the walk. So we expect that if you look at the maximal graph distance, so this was in E1's talk yesterday, the maximal graph distance, so let's call this process x0, x1, blah, blah, blah. These are the vertices that you visit. If you look at the maximal graph distance you have reached within n steps, okay, graph distance measured with respect to the underlying graph. So if I perform random walk on the guy with large faces, then it's the distance in large faces. And if I perform the walk on the guy with high degree vertices, then I take the distance in this metric. So we believe that this should behave like n to some beta for some beta. Okay? And if you perform random walk on ZD, for example, then you always get beta is equal to half here. Beta is half in the case, in standard case, standard Euclidean case. And that this is called diffusive behavior. Okay? When beta is strictly less than half, you displace slowly, and this is called a subdiffusive behavior. So Ewan has described that in all these models of planar maps with ON loops, blah, 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 then you're subdiffusive with an exponent that is unknown, except in the case of the UIPT. Okay? Right. Let me just state this because I will need it. What is known by a standard argument that is the Varopoulos-Varopoulos estimates, they tell you that if the graph is growing polynomially, and the polynomial growth, then you always have beta less than or equal to half. And this will be the case of almost all the graphs that we look. In this phase, we have polynomial growth, this exponent. In this phase, we have polynomial growth. Not in this one. We've got exponential growth. Okay? So let me describe what we get now, which is the nicest board. These two are very nice. Let me erase this one. So what do we get? Cyril, please wake up and correct if needed. Okay, so A will be between 3/2 here to 5/2, and this will be the beta, the subdiffusivity exponent. So this corresponds to the case of Brownian map or gentle maps. And this corresponds to the case of CRT, continuous random trees. So what do we have? So let's put half here, quarter here, a third, maybe here. So what was known back at the first workshop was a third here. We knew that beta for the UIPT, say, was less than a third. This was the result that I did with Itai a couple of years ago. Right? So the UIPT was subdiffusive with exponent less than a third. But actually, the work that I did with Itai, we extended it with Cyril to get a curve that looks like something like this and goes to 1 here. So that's an extension of the result with Itai that we did with Cyril. You may say, okay, that might be somehow interesting in that regime, but not in that one. Of course, for subdiffusivity, we knew beforehand that we were below half here. But actually, this curve, they describe an exponent which is exact. This is the displacement exponent for pioneer points. So more precisely, what is a pioneer point? A pioneer point is a point that when you walk, if it's a point that you discover that can be linked to infinity, that is, on the new undiscovered region, you call that a pioneer point. And this curve says that after n pioneer points, you are at distance n to the beta. Of course, if you make n step of random walk, you have discovered less than n pioneer points, so you're below. But still, this is an interesting and exact curve.
What is the prime one?
Okay. Sorry. Here, so far I'm on m infinity with large faces. Large faces. Thanks. It will come. Okay. And recently, with some work with Cyril again, we said, okay, there is some epsilon here. We are not at a third for pioneer point. We are at a third, but for subdiffusivity, we are just a little bit below. And we believe, but have not done yet, that our work extends and gives something that is strictly smaller than this curve. Okay. But of course, in the case of triangulation, there is this series of work of E1 and collaborators that pinch this value to 1/4. So this is for UIPT, but not yet for other models like UIPQ or Boltzmann or blah, blah, blah. So, but of course, it is believed that for other models, if you are in this universality class, you should have the same exponent, but it's not proved. So this is E1 and collaborators. Okay. So what did we get? It's not much, right? But we have this as well. In the dense regime, we've got an upper bound of a third. You're below. And we believe, though it's not yet done, that this bound extends in the dilute regime. So here it's dilute, here it's dense. And if time permits, I will give you a glimpse of the proof of this. So we are below this, and of course there is a lower bound that is just given by the volume growth and a trivial upper bound on the resistance, which gives something like, if you start at 1/5, then you have something like this. Okay, so the subdiffusivity exponent is somewhere here. Okay, we strongly believe it's something like that. I mean, it goes to 1/4. It has to start at 1/4 to end at a third. For those who know, a third is really Kesten's result, 86, on the subdiffusive behavior of random walk on trees. If you look at the displacement of a simple random walk on a generic tree, then you get a subdiffusive behavior with power a third. So, okay, near the tree regime, we know we are close to it. So that's one part of the result we have got. And then you may ask, okay, as Tim was suggesting, you may also work on the dual. So let's work on the dual. And now we get something like this for the pioneer exponents. So it's again pioneer points. And we again get the similar lower bound by the volume. So it's not accurate. We can give you the numbers, but it's the curves I'm drawing are just approximations. Okay, again, we believe that the work with Cyril does something like this. And we believe you should start at 1/4. So we pinched the value for the critical case A is equal to 2 because the map here is start growing exponentially, start looking like a tree, and you are really subdiffusive. You're stuck in big pockets, and so you are subdiffusive with exponent 2. The exact order we don't know. We have not yet looked, but we don't know what's the subdiffusive behavior for the walk on the dew. Right? Questions? Okay, if not, then let me maybe try to give you a very short proof of this. Very, very short. And I hope nice. And correct if possible. Okay, so actually in the dense phase, so I will walk on dense map with large faces. Okay? So let's work on a map with large faces. So I'm on M infinity. M infinity looks like this cactus-like representation, but with faces which are really intertwined like this. I've got 1 hour, right? And you walk on it. So x0, blah, 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 blah. xn is simple random walk on n infinity. The main geometric ingredients that we will use are the fact that there are cut points. Indeed, if you start from the origin in such a map, at some distance, think of the CL picture, at some distance, it's very likely that you have some face, very, very large face, that does something like that. That's one face that comes and stuff like that. That's one face. In the CLE picture, you clearly see this. At every scale, you find a very large face that will enclose your origin. And here you get pinch points. What do I mean by pinch points? I mean that if you want to escape through infinity, which is here, then you have to pass through this exact point. Okay? And roughly speaking, the order of magnitude of this region, let's say, this is distance r. Let's see, r. Okay? Now we have some lemma with Cyril that counts the number of such points. I'm sure you can give a CLE interpretation of that, but we still need to give a proof in the map setup. And so the number of such points is 4 minus 2a. There are 4 r to the 4 minus 2a such pinch points. So there are a lot. And you see that when a is equal to 2, you have no pinch point, and when a is equal to 3/2, you've got roughly r pinch points, meaning you're almost on a tree. Okay? And now you say, okay. Now you say, okay, let me, I will do the proof in expectation, let's say. Think of TR, the typical time it takes to escape the ball of radius R. Okay, so after TR steps of the walk, you have escaped distance R. That means that by this silly argument, you have visited r to the 4 minus 2a pinch points. And let me be a bit more precise. I will call these points R pinch points, meaning they are pinch points at scale R, meaning that if you sit on red, then red disconnects infinity from a pocket, and this pocket has size R. Okay? And all these points, they are R pinch points. Okay, now we use stationarity. What is stationarity? Stationarity means that if you reroute the walk at every fixed time in advance, say you walk for 1 billion steps, you stop at 1 billion, then the environment you see is the same as the environment you had at the origin. Okay? So that means that TR, the number of times, the number of steps times the probability that the origin is R pinch point. What is this? This is in expectation the number of R pinch points that you've seen during these TR steps of. Okay? But if you pretend that by that time you have escaped the ball of this R, then this is larger than R to the 4 minus 2a, because you must have visited those points. Then you do a computation, easy, and you see that you can compute this because this is at the root and you have a description of your map. And this is 5 minus 4a. Should I look at my notes? Okay, let's try. Five minus 4a. Okay. You do your computation and you see that this probability. This probability is decaying at R. Hence, TR is larger than R to the 2a minus 1. Is that correct? Seems correct. But no, 2a minus 1. 2a minus 1. When a is equal to 2, you get indeed that TR is larger than R cubed, so it's the 1/3 for the subdivision exponent, but it degenerates here to R squared. It's not quite the bound that we have. But then you put stop, because you say, but if the walk has escaped, the walk was doing something like that, and it has escaped. It's very unlikely that the walk has been through this pinch point like straight. You see a pinch point and then bye-bye, you don't see it anymore. Of course not, because if you flash the walk on this pinch point, that's a walk on the pinch point. And then you've got a graph, which blah 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 blah, you use Cantor-Poulos. It's a graph with polynomial growth. You use Cantor-Poulos, and the walk is diffusive on these pinch points. So you don't visit R to the 4 minus 2a such pinch points, but actually the square is easy. Now if you put square here, you get that TR is always larger than R3. So it's a very simple argument, just using pinch points. And actually, there is the same type of argument that gives in 2 lines the third subdiffusivity exponent that I got a couple of years ago with Itai. You can use a kind of stationarity argument without peeling, without just stationarity and kind of geometric identification of points. So, okay, I won't enter into more details, and thank you very much for your attention.
For your last one, probably ideologically not very difficult, but probably practically very unpleasant. But is it probably possible to show that the curve will be strictly below, because in between each of the points, space to get lost.
Really a first look. I mean,
probably push it down a bit.
Yes, probably. If you flat the walk, then you are even probably. I mean, it's a trade-off. I mean, it's a trade-off. Do we want to write 40 pages to get an epsilon? We wrote a paper, but that was 7 pages or 8 pages to get an epsilon. That's worth it. But I don't know. So sure, but it's the first look. So probably for the follow-up workshop, we have a better understanding.
Do you have any clue about the derivatives at 5.5?
No, coupling the stuffs. So I described the coupling via percolation, but this is a big jump in the length, and
but say for the derivative of 1/3 that you get for your curve there, is it for the
at 1/4 here. What is the derivative here? I mean, monotonicity, continuity. We haven't looked at this because it seems complicated already, and beforehand we want to sharpen a bit more the diagram. Yes.
So sort of a very basic question about this, but when you look at stable maps, you always assume you're in the domain of attraction for alpha between 1 and 2. What happens if you take alpha between 0 and 1 instead?
You cannot. If the root face of n infinity as decays like this, if A is below 3/2, this is not a probability measure. So you cannot.
I see.
There are no stable maps. It's really complicated. It's not technical. It's really it's like CNE. I mean, why? Oops. It's the same story. I mean, same, not the same, but spiritually, it's really a constraint that is not clear beforehand. But I mean, nature is done like that.
But there might be maps.
Yeah, of course, you can enforce really large faces map by doing a prescribed degree model, and this is what a student of Gregory is doing, Michael Mazun, if I remember correctly. He takes beforehand very large face that you are given, and then you glue them together and you look what you get, but you then fall in some kind of CRT-like regime, and so. It's not a regime coming from physics. Well, okay, that's fine. Yeah, maybe I should not. No, 10 seconds, rewind. Yeah, it's not a regime that I understand.
So assuming kind of knowledge of fractal dimension, the ON loop model, can you kind of plot the upper and lower bounds that you might get from kind of embedding this random walk in the ON loop model?
You mean going back to to this guy?
So I guess there are some inequalities one can write, perhaps not so good ones, but they relate the diffusivity of the random walk.
To be honest, I have not tried because we really lack one understanding. When we enter a big loop, where do we exit? I don't know. So of course you have bounds, but I've not plotted them because I'm sure they will be really off by a big factor.
Yes, I guess in the graph you wrote there you'll have some.
Yes, especially here. But for you guys, I mean, CLE 4 interpretation, what is the value?
Okay, so yes, Nicolas again, and